Hi there, this is a bit of a different video today. If you didn't know, besides IT projects, I also make physical products. This is an animated logo which I designed for n8n. And I would like to show you today not just how I built it, but also I want to give you insights into the lessons I learned, some material limitations, and the perspective on manufacturability as well as reliability. So let me give you a quick overview of the product first. Let's start with the base, which not only keeps the logo upright in position, but also contains a power button and a custom mainboard. Instead of a tactile switch, I decided to use a capacitive touch sensor. It does not involve moving parts, which not only makes assembly easier, but also reduces the chance of failure. The mainboard is required for power management and holds the microcontroller. More about that later. An aluminum rod connects the base to the logo and acts as a cable channel, so the main board can be wired to a custom LED board. And with some spacing, there is an acrylic glass at the top, all held in place with a custom housing. To keep that together, I used glue in the beginning, but with the larger demand, I switched to pins, which create enough friction to hold both sides together. And some dovetails, which hold the parts together where they would be loose due to the given shape of the logo. At this point, let me tell you that this product is designed for small-scale production, mostly with tools that fit into a private apartment. I actually designed a proof of concept first, which slowly evolved to larger but still small-scale production. So I kept quite a few parts that were good enough and redesigned others which would cut production time and/or costs. And here are the printed parts. They are manufactured with a 0.4mm nozzle and a 0.2mm layer height out of PLA NX2 from Extruder. This combination gives a high quality finish and good material properties, while it remains easy to manufacture even on budget printers. Next up is preparing the 8mm aluminum rod. I'm using a tube cutter to cut it to size properly. During the design phase, I tried different lengths and ended up with 16.6 centimeters, which not only looks good to the eye, but also is exactly 1/6 of a meter, the size of one off-the-shelf rod, so there is no waste. After that, I'm chamfering the outer edges, and later the inner edges with a 45-degree countersink bit. Next up, gluing. That's a solution I needed to go with instead of using screws, but more to that later. So to avoid drips of glue, I first add some tape to the base here and carefully cut out the hole where I can later insert the rod. I'm using CA glue, which not only creates a strong bond, but is also very good at filling the tiny gaps between plastic and aluminum. The same is also necessary for the inner part of the logo. To position the back mount properly, I came up with a simple hack, using tiny pieces of filament placed into pre-designed holes. This allows for the convenience to print the parts without any support structures. So I'm first gluing the pin into the part, and then carefully apply more CA glue to the surface so it doesn't squeeze out when pressing the parts together. Less is more in this case. Later, with these pins, I can properly align the two parts and just press them together. After these parts cured for a bit, I can assemble them with the other end of the aluminum rod. It is very crucial to make sure that everything is properly aligned so it cures in the right position. After a couple of hours, when the glue is fully hardened, I can now remove the piece of tape which protected the plastic from excess glue, and this part is done. Just for reference, this is the approach I tried earlier. For better repairability, I used screws to hold the rods in place. For that, the rods needed to be drilled and tapped. However, it turns out that M3 screws in an 8mm rod with a 1mm wall thickness are just not strong enough. The material is just too weak to withstand shear forces, and while it technically works, the tolerances of the plastic parts and the aluminum rods have to be just right, which is very hard to come by, because there are always manufacturing tolerances, at least for the aluminum rods. So that's why I then got back to gluing again. There is nothing worse than shipping a unit to the other end of the world and soon after it breaks. Now let's take a closer look at the mainboard. This is a Shio Seed Studio with an ESP32 C3 on board. Very compact design, but it only supports peripherals running on 3.3 volts. So that's why I added a logic level shifter to convert the LED data signal to the required 5 volts. For smooth operation, the LEDs also require an inline 470 ohms resistor and a 470 microfarad capacitor wired in parallel. These are the connectors for the LED board and capacitive touch sensor. Then a few pull-down resistors to avoid unwanted interferences. Without that, I had some flickering of the LEDs during boot up caused by the capacitive touch sensor. A DC power jack 5.5 by 2.1 mm for the power supply, and a tactile switch. This is the actual board layout with some thicker traces for the power connections. At this point you might be wondering why not just use a USB port to both charge the device and load the firmware onto the microcontroller. In the beginning I didn't actually know how much power consumption the LEDs would take. Turns out if they run at only 10%, yes, you heard me right, that's all they need for this project, they consume way less power. So the full capacity of this board is not used. However, I kept this design because otherwise I would have had to redesign the entire board, which always carries risks, and the small scale didn't justify investing more resources. Now in 3D view, except for the microcontroller which is missing here. This is a JST VH connector for the LED board and a 3-pin header for the capacitive touch sensor, which is actually angled, just not showing correctly in this view. Also, check this out. The tactile switch can be actuated from the bottom through a cutout in the PCB. Pretty cool stuff. I actually didn't know something like this would exist. Let's take a look at the assembly. I like to work in batches of 10. First I start with unwrapping all the components and placing them in order. Then I need to prepare the boards to apply a solder mask. The easiest way is to surround the board I want to apply solder mask to by 4 other ones, so I have a larger surface on the same level and it doesn't move around. Then I can use this stencil, which has the cutouts exactly where the solder paste needs to be applied, position it correctly, it's a very crucial part, and then I just glue it down only at the top so it is reusable. Then I can apply some solder paste and squeeze it through the holes with a steel spatula. And this is how it looks like when it's done. Now I can place the components into the liquid solder paste and assure that the parts are aligned correctly. Especially the microcontroller and the DC jack are very crucial for positioning because they have to fit into the plastic housing later. Also, I need to make sure that the tiny components are well placed on the tiny pads. Usually the best practice is to place the small components first and then the bigger ones. But I found that this order is the most efficient one and the easiest to work with in this case. Now the boards can be put on a hot plate, and when slowly rising the temperature as given in a datasheet of the specific solder paste, in my case it's 170 degrees Celsius for a slightly lower melting solder paste, it slowly begins to melt. At the end of the heating cycle I need to quickly pull the boards off of the hot plate so they can cool down, the solder paste can solidify, and all the components get well connected to the board. So that was the SMT part, but there are still 2 through-hole components left which need to be soldered by hand. For that I'm preparing the 3-pin connectors which are used for the capacitive touch sensor. And then here are the JST connectors for the LED boards. To speed up the process I have built this jig where I can just place the 2 connectors into, Then put the board on top and just solder the connections right away. I think it's a huge improvement since both hands are required to solder these components, and it's very difficult to hold the components in place with helping hands or fixing them in another way. And as you can see, they are perfectly positioned on the board. Only one piece missing. The onboard microcontroller comes with Bluetooth and Wi-Fi support, and that requires an antenna. This feature makes the product IoT ready. Why just ready? Well, I couldn't come up with a really sensible use case so far. But in case you have a great idea, please let me know down in the comments. For the capacitive touch sensor, I use a TTP223, which is available as an off-the-shelf component and comes on a tiny PCB. These little connection holes are actually designed for through-hole components. But since I'm soldering wires and I don't want the solder to flow through the hole and form a bump, I apply some Kapton tape at the back. I found these 3-pin wires with pre-assembled connectors, which saves me from crimping them manually. To cut them to length, I like to use some tape where I can just draw down the measurement I need and then easily cut the wires to length. It helps to repeat this process very efficiently. I'm doing 10 at a time here as well. Then I prepare the wires one by one using a wire stripper, and before soldering it to the board, I twist the strands and then apply a bit of solder to the ends. And now I first apply enough solder to the pads so the holes get soaked with it. After that, I'm doing a second pass to ensure there are no air bubbles in it, and I get a small bump at the top. Onto that, now I can just place the prepared wires by just reheating the previously applied solder, and since the PCBs are still connected as a panel, it's very convenient to solder them in an entire batch. Afterwards, I can just remove the Kapton tape and break the single boards apart. One last step here. I need to get rid of the onboard LED because otherwise it would shine through the white plastic housing. I could desolder it, but guess what? Clipping it away is just way faster and does the job very well. Now off to the cable which connects the main board with the LED board. Again, I'm using tape to mark my measurement, so I can just very quickly cut all the cables to length. And since I'm using the JST VH connector on the board, I also need to crimp the fitting connector to this cable. This starts with stripping the wires. The length of that is crucial here. Too long and it blocks the connector, too short and it doesn't create a good connection. Actually, I tried getting pre-assembled wires, but the isolation was too thick, so it wouldn't fit through the aluminum rod. That's why I need to make custom ones. So later I can insert the tiny pin into the crimping tool, twist the strands a bit, and then just place it into the end and crimp the tiny pin. Repeating it for all three, and then the ends can just be pushed into the plastic housing. In the right order, of course. Off to the LED board. The schematics are very straightforward. Power is wired in parallel, data in series, plus a small cap next to each LED to guarantee a smooth operation. The board layout was more of a hassle though. Turns out circular shapes are generally more difficult to design and manufacture. Rotating the components along the shape of the PCB doesn't just look better, but it was actually mandatory due to the lack of space. Sounds easy, but it is pretty time consuming. I went with SK6812 LED chips since they are higher quality, but turns out the cheaper, more common WS2812 would have done the job as well. And this is how it looks like coming out of the factory. I used an SMT service for this. Very high quality. Originally, I tried using off-the-shelf bendable LED strips here, but the shape of the n8n logo makes it particularly difficult to use them. Soldering those for larger batches would be everything but economic. Now off to the final assembly. First step is to pull the wires through. I have to admit it's a quite fiddly job here because the aluminum rod is so tight. And since I'm not using the screw technique here, but instead the rod is glued in place, it's quite a tight of a fit around the corner. But with the right tools, it can be done quite well. And yeah, just need to pull the wires through till the end. After that, I can also strip the wires at this end. And you might have guessed it, I'm also applying some solder here after twisting the strands. Then I also apply a bit of solder to the LED board. And then I can solder the wires directly to the board. This is necessary because there is definitely no place to solder a connector to the board. Now I can pull the wires back while aligning the board until it touches the plastic housing. As I said, it's a very tight fit. It is almost unnecessary, but I like to add a bit of hot glue in a few spots to hold the board in place. That way it can't move, as fixing it later would be very difficult. With the hot glue, I also fixed the capacitive touch sensor in place. 2 small dots are just enough to hold it very firmly while keeping it easily replaceable. In hindsight, I could have designed a sliding mechanism as well, but then I would have to make sure to get the tolerances just right so it has no chance to slip out. Trying to keep an eye on the cost-benefit ratio here. And with that, now it's time to mount the main board, starting with the Wi-Fi antenna. There is just enough space to glue it in place here. Then connecting the LED board and also the capacitive touch sensor. And while aligning the cables correctly, I can now insert the board into its place and fix it with a few screws. Align the cables the last time and insert the last screws. You might have guessed it by now, the space is so tight that I even had to add a cutout to the PCB just so I could guide the LED cable neatly. Now it's ready for the firmware installation. For that I just plug in the device into my computer. Using the Arduino IDE I can simply select the device and upload the firmware. I don't want to go too much into detail about the firmware, but please don't tell anyone, I vibe coded it. What probably would have taken me half a day in the past was maybe finished within an hour, including a few iterations. Just gave very precise instructions including which LED when and how to animate and how the button should behave. After double checking the code, I asked for a few minor changes and voila, the firmware was finished. It is open source by the way, link is down in the description. Now I can unplug the USB and add the power connection. Then I do a test run by tapping on the button just to make sure that everything works fine before I continue with the final assembly. This is a laser cut acrylic glass, 3mm thick and opaque, so it has a milky finish. It lets 30% of the light through, which diffuses the light a bit, so you can't really see the single LED spots anymore. There is a protective film I need to peel off from both sides first. Now, to mount this, it needs to be inserted into the outer shell of the plastic housing first, because the dovetails give it just enough space to put in. Then, by going around, I can press together the 2 parts slowly, bit by bit. Finishing off with the smaller parts here, they also just click in nice and snug. Now off to the base cover. So here's the tactile switch I mentioned earlier, which needs to be accessible from the bottom. To make this possible, there is also a tiny hole in the cover. So these two parts need to be aligned properly, and then I can just put in the last screws. For understanding, this tactile switch is meant for the IoT capabilities and could be used to reset the Wi-Fi connection. It doesn't need to be triggered often, hence the need for a paperclip or similar to actuate it. Final step is to put on the silicone cap, so users are not tempted to use it to power the device that way. And here we go. Cue the demo. A 2-meter USB to DC cable is used to power the device. Huge thanks to n8n for getting these awesome user manuals redesigned based on their own branding. It really adds up to the unboxing experience. As I said, this product is not designed for high-scale mass production, but that was also not my goal. Actually, I'm not a huge fan of it, because then I couldn't say that this product was handmade in Germany. Make sure to subscribe if you haven't already, so you don't miss out on future projects. And see you next time.